Alright, so here at the beginning of Unit 3, I wanted to take a moment to review what we've already discussed about this topic. Unit 3 is all about chemistry. Chemistry is the study of matter and how matter changes. And if you remember in Unit 2, we did kind of begin discussing some aspects of matter, specifically how matter is arranged into phases, solids, liquids, and gases, and different types of energy related to that. Ultimately, it was all about thermal energy. That's why we discussed it in the energy unit. So I want to start this unit on chemistry just kind of with a review of those ideas. So we had this theory, the kinetic molecular theory, in our last unit, which basically says that all matter is composed of small particles, and those particles are in constant random motion. That motion is a type of energy, kinetic energy. That kinetic energy of particles in the system we refer to as thermal energy. It's a form of energy. It can flow, it can be transferred from object to object, system to surroundings, and it can be transformed into other types. A related idea was temperature. Temperature, we said, is just the measurement of the average kinetic energy of a particle in a system. It's not a form of energy, it can't flow, but it gives us an idea of the average energy of the average particle in a system. So we had diagrams that look like this. Here you can see I have two systems, A and B, made up of particles. The particles are moving. The particles in system A are moving faster, so their kinetic energy, their thermal energy is larger than B. The average particle here has more kinetic energy, so the temperature is larger. If I put these two together, what's going to start happening? Well, the high energy, fast-moving particles in system A are going to begin colliding with the low energy, um, low thermal energy particles, the slow-moving particles from system B. Those collisions result in what we refer to as heat transfer. This particle is going to collide, transfer some of its kinetic energy to this one. This one will then fly off with a little bit faster motion. This one will fly off a little bit slower motion. So this system is getting colder. This system is getting warmer. And these collisions, transferring heat, conducting heat, will keep occurring. And I'm going to have heat transfer until what happens? Until both systems reach the same temperature. That's known as thermal equilibrium. I'm just trying to remind you guys, give you a review of the idea that all matter is composed of particles. Those particles are in constant random motion, and that motion has something to do with thermal energy and with temperature. These are things that we're going to have to keep in our minds as we go forward with our chemistry unit. All of this related to the idea of phases of matter, solids, liquids, and gases. So I just kind of made this chart to summarize everything that we know about these. We know that solids have a very orderly, structured arrangement. Why? What is holding the particles of this solid together? Strong and effective intermolecular forces. Hopefully you remember that phrase. These are attractive forces between the particles of a substance. So this solid here, and any solid, has very strong and effective intermolecular forces holding the particles together. Liquids have a little bit weaker intermolecular forces, still strong enough to keep the particles together, not strong enough to lock them in place. So the particles are capable of flowing over and around each other. Whereas gases pretty much have non-existent intermolecular forces. They're liberated. The particles are free to completely fly off from each other. This is why gases take up all the volume of their container. The particles spread out from each other. Then we have this idea of phase energy. Phase energy, we said, was a type of potential energy in the system. Remember, potential energy is all about how the particles or how the parts of a system are arranged. These are all attracted to each other. They're all close together. They have coherence. And so we said that corresponds to very low amounts of phase energy. This would be a stable system. Gases, on the other hand, they have nothing cohering them together, no intermolecular forces. So therefore, their phase energy, their potential energy is very, very high. This is a kind of a chaotic, unstable system. The liquid is in between. It has moderate amounts of phase energy. And we had our LOL diagrams that we could use to analyze a situation where a system is changing. So here's an example. Cold ice is melted at room temperature. The first step is always to define the system. H2O is my system. And then I'm thinking about these two types of energy. Thermal energy, which again is a type of kinetic energy. The phase energy, which is a type of potential energy, dealing with how the particles are arranged in the substance. So I'm going to start off with very low amounts of thermal energy. Why? Because the system is cold. And how much phase energy am I going to begin with? Well, it's ice. It is a solid, so the particles are very orderly, very structured. The intermolecular forces are strong and effective, locking those particles into place. The closer the particles are, the more they're locked into place, the lower the phase energy. So that has low amounts of potential phase energy. And at room temperature, I know eventually this whole thing is the system and the surroundings are out here. This would be like the room air. Maybe if it's sitting out on a countertop, it'd be the countertop, something like that. So I know that the whole thing, the surroundings and the system, have got to reach thermal equilibrium. So I think we said that room temperature is represented with 2 bars of thermal energy, just like this. How much phase energy is the system going to have? Well, the particles in my liquid are more spread out. The intermolecular forces are holding them together are weaker and more ineffective. So that would represent moderate amounts of phase energy. The potential energy there is a little bit higher. What's the last thing I need to do in my diagram? I need to show that energy has flowed in from the surroundings to the system. I started with 2 bars, I ended with 4 bars, so I need to show 2 bars flowing in to the system to account for the fact that the system has warmed up and that it has changed phase. So all this should have been review, but now I want to introduce a new way of talking about this exact same process. And this is through using something that is known as a heating or a cooling curve. Every substance on Earth has its own unique graph to show how it heats and cools and to show how it changes phase. So we could replace that word curve with the word graph if you would rather. On the x-axis of these graphs, we have heat energy added to the system. And on the y-axis, we're going to have the temperature of the system. Let's imagine that I have a collection of ice, of water, and it's solid. And I'm going to add heat energy and turn that into a liquid. And then I'm going to keep adding heat energy and turn it into steam, turn it into a gas. This is what the graph would look like. Temperature on the y-axis, heat added on the x-axis. Let's imagine that I'm adding heat at a constant rate. It's on a stove top or something. I have a pan full of ice on the stove. I don't know why. I'm a crazy person who puts ice on the stove. So I'm going to start at a very low temperature. And as I add heat, what's going to happen to the temperature? Well, very clearly it's going to rise. At some point, I'm going to reach a magical temperature, which is 0 degrees Celsius. And hopefully you can tell me what happens at 0 degrees Celsius. Can you tell me? Yeah, the ice begins to melt. Well, I want you to think about this. I'm going to keep adding heat energy to melt the ice, but is the temperature going to increase? No. What happens during a phase change, when you have reached the phase transition temperature, this is the melting point, if you keep adding heat energy, so if we had ice in a pan on the stove and we had a thermometer in there telling me the temperature of the system, I would see the temperature climbing. As soon as I reach 0 degrees Celsius, even though I'm still adding heat, even though the values on my x-axis are increasing, my temperature, the temperature of the system, will not change. So I get this plateau right here. What do you think is happening? I'm still adding heat energy, and yet the temperature is not increasing. So what's happening? Well, remember our LOL diagrams for melting ice. We had thermal energy, and we had phase energy. Started with 1 bar of thermal, 1 bar of phase. That was for ice, for solid water. Over here for liquid water, yeah, it's going to be warmer, but what else increased? The potential energy, that phase energy. So On my graph here, as I add heat energy, as soon as I reach a phase transition, the melting point is 0 degrees Celsius, as I keep adding heat energy, I am not increasing the thermal energy anymore. What am I doing? I am increasing the phase energy. The energy is going into the system to break apart the intermolecular forces. So remember, let's say that this represents some water particles, and let's say that this represents the intermolecular force between them. For a solid, the intermolecular force is very strong and effective. For a liquid, the intermolecular force is weaker and more ineffective. So I have to put energy into the system to pull the particles apart like this and weaken the intermolecular attractive force. I have to put energy into the system to overcome the intermolecular force and weaken it, loosen it up, so that the solid may become a liquid. So on my graph, as I'm adding energy here, the energy is not going to increase the thermal energy of the system to speed up these particles. Rather, the energy is going in to tear them apart, to loosen and weaken the intermolecular forces. So this would represent a phase change. This is where I'm going from a solid to a liquid. Down here on this part of the cooling curve, it was just a solid. I'm just heating up a solid. I'm getting those particles to vibrate faster. The temperature's going up. As soon as I reach that magical temperature of 0 degrees Celsius for water, I keep adding heat energy. My x-axis keeps going up, but it's not thermal energy. The temperature is not going up of my system. It's phase energy. Energy is going in to tear apart those particles, to increase their potential energy, to loosen, weaken the intermolecular forces. So once all of the ice has been melted, remember, if we actually were doing this on a stove top and we had a thermometer in there, we would see the thermometer not move away from 0. As all of the ice melts, the solid goes to liquid. So now here at the end of this plateau, I have 100% liquid in my pan. If I keep adding heat energy, what's going to happen? Well, now the energy will be thermal energy once again. The temperature of my system will increase. So this part of the curve just represents where I just have pure liquid. I'm adding heat energy, heating that liquid up until I reach another magic temperature, 100 degrees Celsius. Hopefully you all know what happens at 100 degrees Celsius. What happens? Water starts to boil. So imagine this. I have added heat energy. The system has absorbed that as thermal energy. My liquid is now moving faster, 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 until I reach 100 degrees Celsius. What magical thing happens there? The system will start to boil. The liquid will become a gas. So let's look at this liquid diagram. I have this intermolecular force. What would a diagram of two water particles look like for a gas? Well, they're going to be very far apart from each other, and they're going to be moving incredibly rapidly. And should I draw intermolecular forces in this diagram? No, gases have virtually no intermolecular forces at all. So think about this. What is my graph going to look like while I am transitioning the system from a liquid to a gas? That's right, I'm going to have another plateau. And it's going to be a longer plateau this time as I go from a liquid to a gas, because I'm putting energy in not just to weaken and loosen the intermolecular forces and raise the potential energy of the system a little bit, like last time, but now I have to do what? I have to completely break and overcome those intermolecular forces, don't I? Yes. So it's going to take more energy to do that. More energy has to go in to raise the phase energy, the potential energy of the system from liquid to gas. Remember, the phase energy of a liquid is 2 bars, solid is 1 bar. What was a gas? It was 4 bars, right? So yeah, we're going to have to increase the phase energy of the system even more, the potential energy. I have to overcome, overpower, destroy the intermolecular attractive forces.